Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh. Shalom, Namo Buddhaya, greetings of goodness and greetings of harmony. Good morning, afternoon to my first and honorable electors. Please allow me to introduce myself. My full name is Theresia Raina Kidi with student identification number 25110210016. A second semester student from the Educational Technology Study Program. On this valuable occasion, I will present a highly crucial topic in network infrastructure, namely IP address and network compilation. This material was prepared to fulfill the assignment for the database and computer network course. Under our esteemed supervising lectures, Dr. Putu Putrini Mahadewi SPD MS, and Mr. Adrianus Iwayan Ilya Yuda Sukmana Eskom MPD. Before we dissect the material slide by slide, let us first look at the concept map or mind map that I have compiled as a comprehensive representation of my understanding regarding IP addressing. Within this mind map, there are 8 main pillars that constitute the architecture of network addressing. Pillar 1, definition of an IP address. An IP address acts as a host identifier in the TCP/IP network protocol that is globally unique under the coordination of the global body IENA. Pillar 2, comparison of IPv4 and IPv6. The comparison between these two generations of IP is viewed through their number of 32 bits versus 128 bits. Routing efficiency, mobility support, IP6 security accepts manual or automatic configuration, up to the quality of service QoS. Pillar 3, address components. The basic structure of IPv4 consisting of 4 octets or 32 bits, which are strictly divided into two parts: the network ID as the network address and the host ID as the device address. Pillar 4, IP address classes. The classification of IP address by EANA based on network size, ranging from Class A for millions of hosts, Class B for thousands of hosts, Class C for small networks, Class D for multicast addresses, and Class E for experimental purposes. Pillar 5, Spatial Address Types. Introduction to spatial address types such as the network address for network identification, broadcast address to send data to all hosts, loopback address 127.0.0.1 for local testing, as well as the domain separation between private IP for LAN and public IP for the global internet. Pillar 6, number conversion. Essential number conversion methods in networking, such as the divide by 2 method to convert decimal to binary and the unit table method for binary to decimal. Pillar 7, subnetting, a network segmentation technique for efficient address allocation by utilizing a subnet mask to distinguish between net ID and host ID through either downed decimal notation or prefix select. Pillar 8, consideration for IP address assignment, factor that must be considered when assigning IP address, ranking from estimating the number of computers, specific point-to-point connection, the choice between static or dynamic IP using DHCP, up to network troubleshooting needs. That is the complete framework of our material. Now let us dictate this thoroughly one by one through the presentation slides. We begin with the second slide, which has a sampling title, "The DNA of the Internet, the IP Protocol." Here we can analogize an IP address as a device digital passport. There are three essential points on this slide: TCP or IP protocol in distributing data globally. IP does not work alone, but works in tandem with the TCP protocol to route data packets. Unique identity: every device that wishes to connect to the Internet requires a strictly unique and global identifier so that data packets are not missent. Governance: the allocation of these addresses is centrally coordinated by a global governance body named IANA or Internet Assigned Numbers Authority to prevent address duplication worldwide. The third slide brings us to the battle between two protocol generations. The class the class of generation IPv4 versus IPv6. We can logically compare their differences through several parameters. Capacity: IPv4 is only based on 32 bytes, which limits its quantity to around 4.3 billion addresses. Meanwhile, IPv6 is based on 128 bits, which can accommodate up to 3.4 times 10 to the power of 38 addresses, a massive amount for the future of the Internet. Configuration: IPv4 is configured manually or by using DHCP, whereas IPv6 supports stateless auto-configuration. Routing: in IPv4, the routing process can slow down because its header size varies with a base for 20 bits. Conversely, IPv6 has been optimized with a fixed header size 40 bits. Security: the IPsec security feature in IPv4 is optional, whereas in IPv6 the IPsec feature is built-in mandatory. Quality of service (QoS): IPv4 uses a standard best effort management, while IPv6 brings a level effort Michael known is us. Describe the anatomy of IPv4 on the first slide. An IPv4 address has a total of 32 bits structured into 4 segments or 4 bytes. As shown on the slide, the decimal address 198.133.210.16, when translated into machine language or binary, is represented by a sequence of zeros and ones across 32 characters. Each segment or single byte consists of 8 bits which have a decimal value range from 0 to a maximum of 255. Moving on to the fifth slide, there is one golden rule that must be understood. It is the golden rule: network versus host. To simplify understanding, we can use a straightforward analogy. Network ID is analogous as the street name. It functions to determine to which center or network the data destination is sent. Host ID is analogous as the host number. It functions to specifically identify which device is targeted on that street. In the IP example 192.168.1.10, this combination numbers will technically separate which portion is the street identity network and which portion is the device's host number or host. The six slides present the IP class matrix. EANA devices IP allocation into several classes based on the network scale recorded by an organization. Class A has a first contact binary range from 1 to 126. The format is network host. This class is instead for Arabian scales because it can accommodate around 16.7 million hearts. Class B has a range from 128 to 191. The format is network. Host it network host. It is capable of accommodating around 6,534 hosts. Class C, the range is from 192 to 223. The format is network host. It is intended for small networks with a capacity of only 254 hosts. Special classes there is Class D 224 to 239, reserved for multicast purposes, and Class E 240 to 255, allocated specifically for experimental or research needs. On the seventh slide, we are introduced to reserved addresses that are present and cannot be used by regular hosts. Network address occurs when all host bits are set to zero. Its function is to identify the entire network of routing purposes across routers. For example, 167.2.05.0.0 broadcast address occurs when all host bits are set to 1. Its function is to send data packets to all hosts within that network simultaneously. For example, 167.205 as the network ID and 255.255 as the host ID. Loopback address: this is the static address 127.0.0.1. Its its function is very unique, which is to return data packets back to the sender itself to test whether the local TCP or EP protocol stack on the computer is running correctly. Next slide explains the division of network limbs, public versus private domains. In a local area network or LAN, we use private IPs. Their characteristics are that they are free and unroutable on the public web network. For instance, the address 192.168.1.10. When we want to serve the public internet, we need a router that has an official public IP registered with EINA. Public IPs are scarce resources and require payment. At the bottom of the slide, we can see the standard private IP ranges based on the RFG class A in the range of 10.0.0.0 prefix 8, class B in 172.16.0.0 prefix 12, and class C, which we most frequently encounter at home or school, namely 192.168.0.0 prefix 16. Entering the ninth slide, this is where the real problem in the world of addressing areas waste and vulnerability was imagining a company that actually only needs 30 IP addresses for its computer. If we give them a standard class C IP, they will receive a total of 254 host slots. As a result, 224 IP addresses are wasted and cannot be used by anyone else. Security A broadcast domain that is too large and massive will make the network vulnerable to cascading failures. So, what is the solution? The logical solution is subnetting, which is the technique to break down a large network into smaller, isolated subnetworks tailored to actual needs. How do we perform subnetting? The main gateway is on the 10th slide, which is using a filtering tool called a subnet mask. A subnet mask performs a computer logical and operation to separate the network portion from the host portion. The ground rule is very simple. Bit set to 1 mean network, will bit set to 0 mean host. Based on RFJ 950, the default mask for Class A is 255.0.0.0. Class B is 255.255.0.0 and Class C is 255.255.255.0. The 11th slide demonstrates the actual mechanics of subnetting, namely the technique of borrowing bits. Let's take a case study of PTXYZ, which requires 5 departments each, containing 30 computers. The network-based usage is class C192.168.1.0. Let's calculate mathematically. To accommodate 30 hosts, we need 5 remaining bits with a value of 0 at the very end, because to the power of 5 minus 2 equals 30. The concrete step, the network will borrow 3 bits from the host portion which originally value 0. As a result, notation which should have been a /24 prefix or before change to a /27 prefix or after. The namely created mask now becomes 255.255.255.224. The results of the bit borrowing technique can be seen on the 12th slide. Divide and conquer PTXYZ's network has now been neatly optimized using the subnet mask 255.255.255.224. We have successfully allocated 5 separate subnetworks, each isolating 30 hosts. Subnet 1 runs in the range of .0 to .31 with network ID .0 and broadcast address .31. Subnet 2 runs in the range of .32 to .63 with network ID .32 and broadcast address .63. Subnet 3 runs in the range of .64 to .95 with network ID .64 and broadcast address .95, and the remaining block spaces are allocated as reserves or reserved units. Through this method, we successfully achieve maximum efficiency with a minimum rate of address postage. The 13th slide reminds us of a fundamental tool in this calculation, namely the toolbox of binary to decimal conversion using the 8-bit rule. The way it works utilises a decoder rule with place values based on powers of 2, 128, 64, 32, 16, 8, 4, 2, and 1. The logical rule: if a bit values 1, then add its positional value. If a bit values 0, then simply ignore it. For example, the binary number 11000, since the first two bits value 1, we just add 128 plus 64, so this decimal result is 192. Before moving to conclusion, the 14th slide summarizes this simplified working process into a structured cycle called the network design cycle. There are 4 stages of the cycle here: assessments, host count, estimating and analyzing the required maximum number of computer machines, but both for current conditions and future projections. Selection our IP class, selecting the most proportional private IP class that fits the scale of needs from that assessment result. with her class E, B, or C subnet, calculating the most optimal subnet mask to isolate divisions of or departments allocation DHCP or static executing a precise address distribution, which means providing static for crucial devices like servers and automatically providing dynamic EPS via DHCP to regular client computers. As a final conclusion, this material on IP addresses and network configuration underlines that building a digital identity within a computer network involves a steps far deeper than merely assigning rows of artificial numbers. Given the limited number of IPv4 addresses, the implementation of subnetting techniques becomes a vital tool to optimize resource usage, reduce IP address wastage, and boost network security through interdepartmental isolation. The success of this actual implementation highly depends on our strong understanding of IP architecture or the separations of network versus host ID and I disciplined adherence to the network design cycle. Before I conclude this presentation session, allow me to convey a beautiful closing quote. The best technology is the kind that brings people together. I hope today's session has been beneficial for all of us. Thank you for the firm attention, first and honorable lectures. I close this presentation with Paramasanti. Om Santi 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 Om and have a great day ahead.